And it's running. Okay, so welcome to the 10th lecture on privacy preserving natural language processing. And today, so on a request of you, we're gonna talk about. So we're talking what should be the topics we should cover here more, and one of those is something called machine unlearning. So you've heard of machine learning, I guess, because this is the standard thing everybody's using. Supervised learning and things like that. So what the heck is machine unlearning? So I mean, it's some sort of opposite of learning, but what exactly we'll talk about today. How is it related to privacy preserving NLP or privacy preserving stuff? I mean, obviously, if you learn something, as we saw in the previous lecture, if you learn something, it will be stored somewhere in the model, and maybe that's not a good thing. So you want to somehow undo it. So it's somehow like postdoc methods for protecting privacy, but maybe even more. All right, so recap. Yeah, well, I don't know. I mean, this is like, okay, so you've seen this all before. We spend quite a lot of time talking about differential privacy. So differential privacy is a go-to thing to, if you can use it while training or while creating data or while doing something, answering queries, that's great because it gives you some guarantees. I mean, these guarantees, epsilon and delta, are probabilistic. So there is a chance something will not work or will work, but they are there. And we talk about mechanisms, and basically the most important part is this DPSGD thing. So how can you train a model, and what assumptions are required for training a model that it will not leak more than you allow it to leak? So there are some formal guarantees on training the model. So this is so far all good, but maybe sometimes you have a model already and you want to just undo a thing. So why is unlearning? So I have to say, like, I took inspiration from this for this lecture from this very nice blog post by Liu. So this is some sort of like high-level introduction, and I highly recommend to read it through. So I mean, they're covering a little bit different focus, but as a kind of overview of machine unlearning in 2024, that's the title of the blog. It's really well accessible. But anyway, so why should we think about unlearning in the first thing? So we wanna get rid of, so edit away undesired things from a pre-trained model. Okay, so what could be the undesired things? Obviously private data. So do you know what GDPR gives? What does GDPR give you, among other things? What is it? There is a thing which you can apply if you're using GDPR. So everybody knows what GDPR is, I guess, in this room. So what GDPR is guaranteeing you as a person, as a citizen of EU, for example. What can you do with the GDPR? So if you can, yeah.
Request the data the company or individual organization has of you.
You can request the data the company has about you. That's right. You can even request more. Not like to know what they have about you, but you can request. You can request the deletion of your data. So this is the right to be forgotten. You can request anyone to forget about you, which means deleting anything related to your person forever, ever, ever. Nice. This is nice. I mean, actually, I talked to some people this week who did this for Google and Web Archive. So they wanted to do something to be deleted, and it works in some cases. The thing is, once you become a part of ChatGPT or Llama 2 or whatever, then it gets a little bit tricky because you've been somewhere in the training data and your data are somehow stored in the model. But still, you have the right to be forgotten. So there has to be a way to do this. And maybe you want to get rid of some obsolete knowledge or some copyrighted materials or some unsafe, dangerous capabilities. What could be dangerous capabilities of trained language model? It's an arbitrary decision. So maybe how to build a bomb people consider as a dangerous capability of language model. But in some cases, it could be a good capability of the language model if you're learning something about, I don't know, rocket science or whatever. So that's a thing. But the private data and copyrighted materials are kind of things that everybody is agreed on. So this could be should be able to unlearn from the model. The thing is, yeah, without retraining the model from scratch, of course. I mean, you have a data set, you have the internet, and you want to be removed. What you do, I mean, is if you were the company, you just say, well, sure, I'm going to delete all your files or the record from the table. and call it a day. And then you have to retrain all your models from scratch. This is the most simple solution, and actually the only one which is like provable right. If you delete your data and train the model again, you are not in the model anymore. Done. Awesome. But it costs money and time. So there might be other ways or other strategies to deal with that. So what is machine learning? I mean, this is not rocket science. Machine learning means like you are not part of the model. This is it. I mean, this is very easy. So you want to remove the influence of particle training data from a training model, and you want to find an unlearned model that is somehow similar to the trained model, or it behaves like if the model were retrained on the data which are from which the data to be unlearned are removed, right? So this is easy. If you have a data set and there's LEs in here, and you train a model, so then you train a model, then you want some similar model then without LEs. So you want to train, if you remove LEs, you want something almost like that. You know, in terms of accuracy, capabilities, and stuff like that. This is it. I mean, makes sense, right? Okay. And so machine learning is a relatively new thing, to be honest. So this is really part of active research, and there are a couple of strategies which have been used across the places, as we will show later. But it's still a lot of things to be explored or even defined. So this is not cut in stone. Like you have to define what you're actually achieving. And one of the it has something to do with what a machine learning task is. Is it like, for example, binary classification, or is it language modeling? And what you want to unlearn is like set of images or news articles or some knowledge, So here's the knowledge, like knowledge of making napalm. So maybe it's something that you want to unlearn from a model. And that's a different kind of things, because what knowledge means. If, for example, making a napalm is something which is present in like 100 books across your data set, that's going to be harder to unlearn than, for example, just if you have a classification of movie reviews and you just remove one review from the data set. So that's going to be much different in a classifier, for example. Obviously, the algorithm which is going to unlearn, like whether it's some heuristics or something with the model, and of course the goal. Yeah, sure. I mean, is it for privacy or some harmful content? So there's many facets of that. So just I want to make sure that this is active area research and people are defining what they're trying to do with unlearning. So let's talk about some early approaches to machine unlearning. Actually, the first mention of machine unlearning in 2015, I guess. Yes, towards making system forget with machine unlearning. So how they coined that is that to forget a piece of training data completely, systems need to revert the effects of the data on the extracted features and models. Okay, so here's a question. So what are features? What do we understand in features as features in machine learning? Any idea? What are features? If we talk about features, what could that be? So we have data set. Okay, so we have let's say we have data set of, I don't know, of documents. Okay, so we are doing IMDb sentiment classification. Okay, so we have review 1 and review 2, and these are text review 3, and we want to classify them into positive or negative and stuff like that. So what are features? Second, so I didn't hear you. The movie name will be feature, maybe, yeah, but is it what you really want to do, like based on the movie name to? Yeah, the ratings will be featured, but if you just have a text and no ratings, you have no features. So what could be the features here? The reviews, yeah, but what exactly? I mean, reviews is a text. So how do you turn text into what is a feature in in machine learning? Okay, yeah, the whole process of converting text into tokens or into a so-called feature vector. Okay, right. So some sort of like super baseline feature vector in NLP, the simple one. So back of words, for example. You were I think you were about to say that, right? Back of words. Okay. So back of words could be one way of extracting features from document. Why they are mentioning here extracted features and models? I mean, models make sense. Models are trained from data, but why features are based on data? Well, you can actually train your so-called feature extractor based on your training data. So, for example, you want to build your vocabulary. If you do back of words, and you don't have any vocabulary set, you don't know which words are going to use. So the only thing, the easiest thing you're going to do is just go through all your words in your training data and collect the vocabulary, and this will be your feature vector. Like, I don't know, there's 5,000 different words, so the feature vector will be 5,000, and then the words are just from the training data. So that's why you also need to take into account you can extract features or feature extractor based on data and models. Okay, and we talk about it. So what would be the easiest method for unlearning? If I want to remove myself on person number 2, I want to remove myself from the model. I'm just going to delete it and train again. That's it. This is the easiest method of unlearning. So retrain the features and models from scratch after removing the data to be forgotten. And we shouldn't underestimate the implications of that. So this is 100% provable. If the data points weren't used for training, they cannot end up in the target model. It sounds like obvious thing, but this is it. And if you want to prove that you are not in the model, well, the algorithm is good. The algorithm just deletes data, which means you are not in there. If you compare it to, for example, differential privacy, so when we are, oh yeah, there's some chance, delta, that I might be in the output, but it will be, compared to another data set, there's some bound on the ratio, which is epsilon to, e to epsilon. Yeah, so this is not proof like 100%, there's some chance. And you have to trust the algorithm, the differential private algorithm, that you are not leaking from the data. Here, if you delete data, 100%, done. Cool. Okay. Of course, the lack of scalability. So when the data set is large, the approach is slow. So do you know how long it takes to train, GPT? Nobody knows. But GPT-2, how long does it take to train? What do you guess? Any guess? What do you think? How much resources you need to train GPT-2? Any guess? So week on one GPU. 2 weeks on? 2 weeks on the 1,000 GPU. Yeah, so no, good luck. More. Yeah, of course. Yeah, I think you need like really thousands of GPUs for half a year, maybe, or a year to train some decent language model. And that's a lot. That's why all these companies are buying. That's why there is a shortage on GPUs. At least last year, this year is getting better, but that's why all these, that's why NVIDIA is getting rich. So if you bought any shares of NVIDIA and didn't sell, good luck. Congratulations. If you bought shares of NVIDIA and sold them, I did that, and that was a bad decision, because now, last year the NVIDIA went up again, and it's getting again because they're building GPUs, everybody's using them, and Microsoft is buying thousands of GPUs just to train language models. Okay, so it's gonna, the market is kind of still not saturated enough. Anyway, that's a tangent. So anyway, you need a lot. So that's obviously, you don't want to repeat this, after I come to you and say like, oh, please, OpenAI, just delete my data. And they say, of course, they would delete your data, and let's train this thing again for half a year for costs of maybe million or even, well, $1 million, I would say, because you need to, electricity bills, cooling, the hardware, everything. It costs a lot of money to train GPT. Okay. So that's a real thing. Okay, so here's what they proposed back then in the first paper. So typically we have, so I think these are the training samples, and typically there is some learning algorithm, which I don't know, maybe it's like a stochastic gradient descent. So it goes through the data set, takes one and updates a neural network, and maybe many batches and stuff like that. So basically it iterates over the data over and over, and updating based on some losses, excuse me, updating the weights of the model. What they here propose something that's well, a few kind of simplifications. So what is important to say, they kind of split the algorithm into some summations. So basically they say, well, we have a couple of transformations of each of these points. So which means each of the point will be somehow transformed into something else. And these transformations should be easy and fast. And then these, they call it summations. So then these summations are, there are a few of these summations which are directly used for the learning algorithm. So there's some sort of, I don't know, like maybe averaging or some parameters of these things that are used in this prediction and training. So it's sort of like feature extractor, and then using these aggregated features for the algorithm. And the assumption here is that these are easy and fast to compute. So which means if you need to unlearn, you just recompute a small number of terms. So if you want to unlearn this, for example, this point, well, you can easily compute all these summations, and then it won't change the algorithm. So the algorithm just uses these as sort of hard-coded features. So you don't have to recompute that. So it's a trick in a way that makes the problem work in some scenarios where you can do this transformation. So we don't go into the details. I mean, this is not about, you know, really nitty-gritty details of these algorithms, because they are not really, they haven't been used really in natural language processing tasks, for example. Some of them are more theoretical as well today, as you will see. But just to see, like, you need to find a, you know, you need to hack the problem around. Like if the problem is too complex, then you need to find a solution maybe which works on some just sub part of the problems. So this was one example. And okay, so each summation is some efficiently computable transformation of the training data samples. Okay, so and the unlearning works that we only recompute a small number of terms, which is faster than retraining from scratch. So this was the idea here. Okay, you need to be faster than just retraining from scratch. If you need to if you are not any faster, then you can just retrain. That's a point. But if you can speed up maybe twice, maybe 3 times, who knows, then you're saving time in the recompute. And it comes with a couple of limitations here, and I think I have them on the next slide. Exactly. So some future work, basically, or some consecutive work on machine unlearning identified as limitations of this first kind of attempts. It's like it works only on very structured problems. And these were problems, without going into details of these machine learning problems, is that you need to be able to transfer your task into this transformation and summation, which doesn't work for, I don't know, for anything you want to learn in NLP or some more complicated functions or models like, you know, neural networks, for example. So it wouldn't work for them. I think they tried it for SVM and naive Bayes. Raise a hand, naive Bayes. Raise a hand. A little bit. Okay, naive Bayes. Okay, it's very simple classifier based on counting and dividing. So you count, you know, numbers and have probabilities, and it's very simple. So naive Bayes is a nice baseline for, you know, many tasks in machine learning, but it's a baseline, so it's not that good as, you know, other SVM. Does it ring a bell? Support vector machines. Okay, cool. Yeah. So they use it for, you know, as far as I remember, they tried with SVMs and naive Bayes as well, but these methods are just now obsolete, you know, with deep learning and large, basically large models. Okay. Good. So these were these limitations. It was like one of the first who coined that. And then, you know, if you think about the problem, then you have to sacrifice something if you try to unlearn. So you don't want to recompute everything from scratch. So maybe there's a way around. I mean, if you in general, like in any algorithm in computer science, you have multiple dimensions. One is time, and there are some algorithms that just go faster, but they need more of something else. What could that be? So what do you need? I mean, if you want to, there are some algorithms that are faster, but you need to do some things in between. What could that be? Any ideas? So if there's, I think, like overall in computer science, you either compute quite a lot over and over and over, or you do something in between. You just store some intermediate results, right? I mean, you're like caching. Everybody knows caching. So you put something in the cache so you don't have to recompute again. The whole thing of backpropagation is just basically caching. Or you just stored some parameters somewhere and, you know, just keep them. And then if you need them again, you just, you know, pull them up. So you're saving time, but you need more storage, for example. And this is exactly what this SISA, sharded, isolated, slice, and aggregated training is doing. So it's shortening the time for deletion. It gives some guarantees, as we will show later, but it comes with their limitations. You need more storage. So how does it work? There's this is interesting. Why there is this unlearning versus differential privacy slide right now? Okay. Because they said that it's different than unlearning is different. It's not a thing as differential privacy. Okay, so let's see. Maybe I'll skip that and come to back later because I want to talk about this SISA thing. Okay, let me just focus on this unlearning with this SISA framework. And let's just look at this. This is a picture from the paper, and here we have a data set D, and we have some trained model MA. Okay, so we have the data set D and fine-tuning a model MA already trained on D. So this is what we have. Then if we add a new model, if you add a new item, so DU to this data set, so like LEs. So we add LEs to the data set, and then on this data set, train basically a new model, right? I mean, we have a data set MA, which is trained with the data set we have, and then we add one more item to the data set, and we train another model on this little bit larger data set. So the model will be different. So we get MB. And now, if what is it? Okay, so this is the data set D and data set D plus DU. Unlearning this thing is hard because there exists no function that measures the influence of augmenting the data set and fine-tuning. Okay, yeah. So basically, the only way you can go from here, from this model to another model, is to store this previous model somehow. Because if you want to go anywhere else, like maybe you add some other data point DW, then you don't know the impact of this particular point on the model. So there is no way to know like what you do once you do that. So the only way is to come back, take the original parameters, and just go somewhere else, right? Like in general, if you do, I don't know, in stochastic gradient descent, you always take a sample and do the computer gradient and do the update, and then you move somewhere in the parameter space. And then if you move somewhere else, and you're already there, you didn't know what impact this point had unless you really travel back and get the parameters of the model. So this is why in general this is hard, because you cannot just undo this learning, because in the parameter space you're moving somewhere always depending on the data point. So this makes it impossible to revert the model ME without saving its parameter state. Okay, that's what I was saying before learning about DU. We call this model slicing. Okay, so slicing means model slicing. So slicing means you have one slice of a model and another slice of a model, which you basically save the parameters for. If you have trained on D, you save the model checkpoints. If you train on model D plus this new item, it's a new model D, MB, and you have to save them because these are different models, and you have to remember how you get there, basically tracing back the path of the training data. Okay, any questions? Does it make sense? Like, why is it hard in general? Like, if you add another data point to the model, another data point to the training, then it influences the resulting model in some way, mostly in some parameter space through gradient descent. All right, so let me see. There's a lot of text. Maybe we don't need a lot of text. Maybe we should go just to the picture, but let me see what's there. Retraining from scratch while omitting data points that need to be unlearned is the most straightforward way to provide probable guarantees. Yeah, exactly. I mean, this is basically, I'm taking this from this research paper, but retraining from scratch is always the option. This is the baseline. I mean, you just delete the data and retrain again. Okay, cool, yeah. So this SISA training replicates the model being learned several times. Oh, interesting. And we have some replicas, which has a subset of the data set. And then in these replicas, there are some, okay, let me just skip this tape because it's not really explaining what, I mean, you can refer back to that if you see the picture, but here's the picture. So let me just skip that, sorry. Okay. So the idea is actually very simple. You know, you would, if you think about like 10 minutes about the problem, you would, I hope you would come up with something similar. So what you do is you have your training data and you split them into these, how they call it, shards, replicas, like, I don't know, something like disjoint sets, right? It's, I think like shards are in some distributed setups. Have you heard of this word already? I guess they use a shards where you have different databases on different machines and they're somehow communicating together. Anyway, so you basically a subset of that. So you have these shards, and each of them is split in slices. Like so there's data point 1, data, or this is like a subset of data points. So 1, 1, 1, 2, 1, 3, and so on. And then for the second shard, there's 2, 1, 2, 2, 2, 3, and so on. So basically like slicing, distributing data and slicing them together. So far, so good? Basically how you split the data. And then the idea is that you start training a model on each of these shards independently. So if you have S number of shards, there will be S number of different models. So, and the way that you, well, so this is one thing. You have basically multiple models for each subset or each shard of the training data. Why not? If you have enough data, each of them will have enough data to train, maybe. That's a one design choice. And then, while training in the shard, you basically start training with some, okay, so there are some assumptions for this, that this training should be some iterative training. But stochastic gradient descent is iterative. You take a first part of the data or batches, update the parameters, then take another part of the data, another batch, update the parameters, and so on. So this works well easily as well, because you take the first part of the data and update the parameters of the model and save it. So basically, you save it. How do I write it? Save. Okay, save it. You save it, save the checkpoints. Okay, you save the parameters of the model. Then you take another part of the data and again save it after training, and you basically save each of these, you know, after each of these copies. So finally, you will end up with a full model here, and you do it for all the shards. Makes sense, right? I mean, this doesn't look like rocket science. Maybe it was, you know, kind of hard to come up with and to empirically try that it really works. So now I come to you and okay, so here's the first question: like, how you have different models for different shards. So if you need during inference, so if I give you like one new example, I want you know, I know classification maybe. So how do you classify that? So how they did that is, or how CSI is doing this approach is that you take you have these different models. So you have your test example, and you run it through all these models in parallel, and each of them will give you some result, maybe yes, positive, positive, and here maybe negative. Because these models are different, so they have different predictions. So how do you get the result from these predictions? The easiest solution. Voting. Which sort of voting?
One which is giving you the maximum results for one.
Yeah, so majority voting. Yeah, exactly. You take the majority of that. So if this were 0 and 1 and 1, so you just take, okay, the majority is 1, and this is your inference. Well, actually, this is a known technique in machine learning in general. It's like, I think it's called ensemble learning. So we have an ensemble, which is just a bunch of different models, and you just do voting. Okay, so ensemble learning is a thing. It's some even like theoretical property. So it's a known concept. So the actual prediction is kind of known. Good. So now how should we do the unlearning? So if I ask you, okay, well, I'm person number, 2.2, which is this data to unlearn. So what do we have to do? How can we solve this unlearning now? I'm person number 2.2, which is this. How do we unlearn the whole model?
train all others.
Exactly. Exactly. This is it. So we say, okay, I'm in this chart. So I'm going to this chart. And I'm going to locate my cell here, which is this data, and I'm going to delete it. Then I'm going to look into the previous model, like the one before, and I'm going to just retrain with the resting data to get a model. That's it. Right? I mean, you look skeptical.
Oh, like if we take all of these trained models, assuming the batch size is big enough, so like the slices are big enough,
Yes.
that they don't change the batch size, if we just do stochastic gradient descent. If we do like the mean of all of the weights, is that equivalent to just training a normal model?
If you do, where we do, so you're, okay, so I just want to understand. So you say you would take a mean of the weights of the models.
They have all the same structure, you could just take the weight.
So you would average the weights of the models. So you would say, you would take this model and this model and this model and average the weights. I think model averaging is a thing, absolutely. They didn't do that. They did just the training and things. I mean, model averaging is, I know it from some sort of uncertainty or Bayesian learning, where you take different models and average the weights to give some certainty capabilities. But I'm not an expert on that. I mean, theoretically, you can average the models. Why they didn't do that? I don't know. So
In that case, you could take the model out of the average, like the model with the data you don't want, and just
yeah. But sure, I mean, but then okay, I see. So you can average the model, and if you retrain the model, you just take it out of the average and just retrain. But that's basically the same as taking the majority. In some way, you can either average the model to give you prediction. So you have one model which is average with weights, or you average sort of the prediction. One way or the other. It doesn't influence the way of unlearning, I guess, because you have to somehow remove the data, or they remove the data and just do the unlearning. Yeah, you have a question.
Run the models separately from each other. So as you already said, in a database context, with
the charts, yeah.
It's so you can run different databases that don't need too much the model.
Yeah, that's right. I think like you can parallelize the several models. I guess the number of models is not that huge, and I think like the runtime is not an issue here. I mean, the issue really is the need for retraining the whole thing versus retraining in charts and retraining where it is. But having multiple models versus one model which is average, I don't know. I mean, it's worth, maybe somebody, I'm pretty sure somebody tried it, like averaging the models here. But the only thing like is that the splitting and sort of the iterative way. And this is provable, like 100%. If you remove the data, it's not in the data again. Okay. All right. So let me just come back to the text because maybe there was something interesting. So CISA training deviates from current strategies in a way that incremental model updates are propagated or shared. So there is no flow of information between constituent models. That's right. So we were talking a little bit last time about federated learning, where you have some local machines running local updates and then sharing the model weights with a central server and sharing back. So there is no sharing between the models. These are strictly separated, just because you have to have them separated. So this is one difference between like distributed learning, for example. And what else? Each chart is further partitioned into slices. We talked about it, where each constituent model is trained incrementally and iteratively with an increasing number of slices. Exactly. So slice and slice and slice. At inference, we aggregate the responses similar to the ensembles. Exactly. And when we need to unlearn, the only constituent model whose dataset contains is affected. Exactly. So we talked about it already. And iterative learning is like a stochastic gradient descent. So this is just basically describing what we are talking about in this picture. And I think this picture is kind of self-explaining in a way. Okay, any questions to CISA? So theoretically, it should be, I guess, clear. Like this is a strategy. And of course, now the question is like, okay, how many shards, how big the slice is and things like that. And this is nothing empirical to be, you have to really work in this task. So in this paper, I guess they have some like theoretical probabilistic, let's say bounds, or kind of estimating if you have random access to the data, how much you save on on unlearning. And I think they show like 2 to 4 times speed up compared to just retraining from scratch, which is great. So 4 times, if you have to spend 200 million, instead of if $1 billion for training, that's a saving money. So that's great. Oh yeah, exactly. So 245 to 5 times for some unlearning task. By the way, well, if you want to somehow get a high-level introduction to unlearning as well, this is a very accessible paper in Communications of the ACM. So like 3 pages, and they're discussing some recent things and basically saying, well, unlearning is still in the early stages. So highly recommend it if you want to get a grip on that. Okay. So the limitations of CISA is that, for example, by reducing the amount of data per shard. So yeah, there's an impact on machine learning, and the lower quality outcome is likely. What does it mean? Yeah. So for example, here, I mean, we know the more data, the merrier. So if you have more data, you will learn a better model. But if your shard is getting smaller, well, then maybe you have more models, maybe, and then it's easier to unlearn because you just need to, just repeat only few slices in each shard. But maybe then each model is getting sort of very weak, and you end up with a bunch of weak models, and even like their average or their aggregation will give you better results. In contrast to, if you recall, or if you ever saw like this learning curves, or the scaling law of large language models, if you feed it with more data, it will just work better. That's it. Like if you feed it with double size of the internet, it just matter. No matter what these sort of tricks in the architecture are, the more data, the better. And here we're saying, yeah, we actually want to feed it with less data because then we can unlearn easily. So you see the trade-off here is not about like privacy and accuracy, but more about like, well, how fast can I unlearn versus the accuracy of these models? So there's again some trade-off. There is no free lunch. Okay. Good. This is the limitation of the CISA. So what are we saying here? So another limitations, yeah. And now we're again like the another limitation, which is more like engineering thing, is that you have to store after every slides, you have to store the checkpoint of the model. So you have to basically, as we just said, like after each of these slice learning, you have to save the model, right? You have to save all the parameters of the model. You have to remember it. The problem is if you have like billions of parameters, well, even like thousands or millions of parameters of the model, it's gonna be huge at the end of the day. So if you have a large model in size of gigabytes, and you have, I don't know, like 20 slices and 30 shards, you need a lot of space. So this is the price you're paying for the fast access, basically. So, and there are clever ways to go around that, as we will see later. Okay, so this was the first part about like something very provable, very concrete. You just remove the data and relearn, but not by learning or training from scratch or everything, but just having some sort of random access to some parts of the data which you just split, and having some. The good thing, I mean, what makes this framework better than the previous one that we talked about, like this works for any sort of network. I mean, you don't have to care about like machine learning algorithm. So it works for neural networks. It could work for SVMs, or something which you can train maybe with stochastic gradient descent. While the first kind of approach was really bound to these particular methods and some structure problems. Okay. Now we're getting, I mean, this is a field which also attracts a lot of theoretical people. So if you don't like what you will see, that's fine. But I just want to share another perspective of machine learning with you. So okay, I hate this already. But no, not really. No, just bear with me. I mean, this is going to be fine because you will see something which you already know on the next slide, I hope. So there is so this paper from 2021, NeoRIPS, so one of the top conferences for machine learning. So they try to go more theoretical about unlearning and do something more than just, yeah, you just retrain from scratch and that's fine, or you just do sharding. So let's have a look. So we have a learning algorithm A and the data set S, and it gives us a model AS. Okay, so far so good. Okay. So then we have another unlearning algorithm A bar, and it takes the model. It takes something which we want to unlearn, which is a subset of the training data. So the training data is everything, and the U could be, I don't know, Elise and Bob, because they need to be removed from the data set and from the train model. So these are data samples that are to be deleted, and this unlearning algorithm should output a new model, which is W tilde. Well, it doesn't make any sense. Why this is A, S, and this is W? I have no idea. This was their decision to name this, like whatever, research. So we have a new model. Okay, so again, this unlearning algorithm takes the learned model, the data which should be unlearned, and should output a new model. And also, this unlearning algorithm can access some additional data statistics. So some statistics about the training data. I'll come back to this later. But the unlearning algorithm does not have access to the entire original data set S. So it cannot retrain from scratch. So this is the assumption or constraint they kind of are following in this line of research. So you have a trained model. You have a subpart of the data set you want to unlearn, and you have some statistics about your full data. So here's the function which takes the data to be unlearned. This is the trained model, and these are some statistics of the data. It could be, I don't know, some number of items, mean, some sort of whatever statistics, some things which you can store. The idea is that this statistics is smaller than the entire data set. If you just take the entire data set, you can just learn from scratch. So you want to make it smaller, but you can have more. But you don't have access to the original data, only some statistics. And it should produce some new model, which is in this W. Okay, so far so good. Okay, so we have this unlearning model, and we have this formalization. So the unlearning model is a function of the unlearned data, trained model, and statistics. Good. So this is what we have. Unlearned model. AS is the learned model and statistics, and it gives us something. Now, of course, we might ask, okay, what is the, now we're getting probabilistic. So what is the probability that the unlearning algorithm will output something? So this is the unlearning algorithm, which outputs some parameters. And what is the probability that this unlearning algorithm will output some parameters? Why not? We can ask what's the probability that it will learn these parameters, so we can think about probabilities. Okay. Do you agree with me? We can ask, like, what is the probability that the parameters are that and that and that and that? Yeah, if we have some probabilistic methods in there, we can ask that. Now, what is S minus U? Okay, so what is this symbol here? Everybody knows that? This is a set difference, so set minus. So you have two sets and you just subtract the other. So S minus U is the original data set after removing samples to be unlearned U. Okay, of course. I mean, we have the data set and just remove these Elise and Bob, for example. Now we can ask, what is the probability of the unlearning algorithm that it outputs some unlearned model as before, but this time the original model and statistics were trained on something where we just remove the data. Okay, so here we basically have no data to be unlearned, but we have a model that was trained already on the data set minus Elise and Bob, and we have some statistics about data set minus Elise and Bob. Does it make sense? So these two are different. This is, we have S here, which is the data set. It trains the model A, S, and then we want to unlearn it to get some V. And here we have the data set, but we removed U. And this will give us the A trained on S minus U, and that's it. We don't want to unlearn something, so we get some weights. Oh, maybe this, I don't know if it makes it worse or better, but these are just two different ways of looking at it. I mean, this has only access to the model trained on full data, and this is model trained on the data minus those to be unlearned. Okay, everybody's following there? If not, just maybe give it some time. Okay, so we have these two probabilities, and they might be different or not. So, I mean, of course, if you train on some data and if you train on some data minus another data, they will learn something else, maybe, or maybe not, with some probabilities. And now, this looks super scary, but you've seen this before. So we have epsilon and delta. Oh yeah, what a surprise. So you know epsilon and delta from differential privacy. And we also know the epsilon delta differential privacy guarantee. So if you just forget this and call this D and this D prime, you see differential privacy guarantees for epsilon delta. Okay, so but this is not differential privacy. But this notion is it's same. And one of the reasons is that one of the authors, Gautam Kamas, is also very active in differential privacy field. But anyway, so the form is the same. And it's saying, well, the model, the first one we talked about before, like the one trained on the full data set with some points to be unlearned, the probability that we're seeing some parameters of that model or some way of the model is a little bit different from the probability that we see it on this model trained on the original minus these points to be unlearned, right? I mean, these are these two things. That's why we discuss them. So this one and this one are a little bit different. So the probabilities that we see these models, these parameters, they differ exactly by some factor plus some delta. Okay, so with some high probability, because the delta will be small, so with high probability, these models will be similar up to some factor epsilon to e to epsilon. Okay, so this is the very same kind of notion as in epsilon delta differential privacy. If we have delta 0, then with probability of 1, they will be different by factor e to epsilon. And why we have this, and this is basically symmetric. So it's as in differential privacy, you have the neighboring data sets D and D prime and D prime and D. So this is the same thing. Basically, this is just symmetry. Okay, so with high probability, we cannot tell whether we can differentiate these two. Why I'm saying this? Because it gives another way of looking. I mean, maybe this is some, I don't think you have to remember any of those, like the formulas, because this is just really active line of research. Why we're saying this is that it gives a different notion of what unlearning means. Like we're not saying, well, 100% sure the data is not there. Yeah, this was the CISA or training from scratch. Here we're saying, yeah, the model you're getting after unlearning will be somehow similar to the model which you get after, with CISA approach, or removing data, like removing data and training the model will be a little bit different, will be different and not the same, but not far away from a model after applying unlearning. So it's saying, well, the unlearning actually has no access to the original data. So, but I can do some tricks, and the resulting model will be almost the same with some epsilons and deltas. So this is cool. So it doesn't give you any guarantee, because the only guarantee would be I have access to the training data, but I don't. But if I don't have access to training data, I can still come up with algorithms that will give me some model which is similar to what I would have if I had access to the training data. Okay, this is the take-home message. Like not the formulas, but this kind of paradigm. And these things are modeled by some probabilities here. Okay, does it make sense now? Okay, cool. And it comes, of course, with some limitations where. So, okay, I don't think this is important right now, but the limitations are that this works for some algorithms or for some training algorithms which has convex loss functions. Okay, so what is a convex function? Oh, okay. we have convex, and there's another function which is the opposite of convex. Do you remember that? Convex function, and the other was, I guess, concave. Does it ring a bell? What is a convex function? So this is a U shape. So convex function is something like this. This is a convex function. And the concave is the difference, like the flipped U shape, okay? So what a convex function means, okay, which convex function, like x squared for, oops. X squared is a convex function, right? So convex loss function, loss function. Okay, we have a, for example, what is it? Square error is a convex loss function because it's squared. Why convex functions are easy for gradient descent? Because you can always go to the minimum, like the global one even. So if you have loss function which is convex, with gradient descent, you will absolutely find the minimum. Awesome, yeah. In reality, neural networks, they don't have convex loss functions. They are just somehow very weird functions of the parameters. So there are no guarantees. That's why this thing doesn't work for neural networks, because neural networks don't have convex loss functions. So, okay, so this is the limitations. I mean, you have some algorithm which is able to unlearn with some probabilistic guarantees, but it doesn't work, it's not a silver bullet. It doesn't solve your problem with neural networks, okay? So that's why this is like super active area of research. Like, will it work in, neural networks or somewhere beyond convex loss functions? Who knows, maybe. All right, so sorry for this theoretical kind of theoretical interlude. Let's go back to something, tangible and doable in NLP, okay? And then we'll finish. So CISA, now we know what CISA is, and surprise, surprise, somebody tried it out on, in NLP tasks, and, just see how it works, which models can be used and stuff like that. So, and this was the work by Bani Hatikunar, Kandara, excuse me, I cannot read his name. Ganga Dharayan and Dan Roth from Amazon Research. So the idea, again, CISA is saying we have these shards. So we split the data sets into the shards, and we have the slices. So it's basically the same picture as we had before, but just differently. And then we have the trained models and aggregation and the label. Okay, so this is the CISA thing we saw before. And the model goes through the data, slides by slides. So here's a model, one slice, and save it. And another slice, and save the parameters. Now, what they're using is the BERT model, okay? BERT. So how big is BERT? Has anyone here worked with BERT like for real? Like you downloaded BERT and tried something playing around? How big is BERT?
Not that big. I think it's like, not sure the download is quick.
The download is quick, yeah, because you have internet is fast these days. It's a few gigabytes. Okay, yeah, I think it's actually a few gigabytes. So there's some million parameters of BERT. I think, I don't know, 300 million parameters, BERT small, BERT large, whatever. So it's not small, it's gigabytes, which means if you have BERT, and again, you have, I don't know, like 20 slices times, 3 times 4, like 12 times BERT, you need a lot of space and a lot of compute actually to shuffle data around in just training or inference. So that's something you want to avoid. So what this research is trying to see, well, okay, CISA works. Like if you want to unlearn this part, then this stays the same, and you just delete this and start again from here and go here and stuff like that. So this is fine. So this main architecture stays the same. So they just added CISA, and they were interested in how can we save time and space, like hard drive space, on saving these models, because you don't want to save BERT or fine-tune BERT every time. So yeah, so this is the unlearning request, which is easy. So pick the shard, and if I'm here, I pick shard, delete, and retrain. So this is not new. So if you train BERT, you can do in many different ways to train a fine-tune BERT. So BERT is pre-trained. If you're not familiar with BERT yet, I highly recommend to get familiar with that. There are tons of resources. Some of them are mine, and there are some thousands better one. So you should know BERT. This is the transformer model trained on basically mask language model. I think we talked about this in this lecture as well. Okay, just so BERT is a big model, transformer model encoder. And if you fine-tune it for your task, you can either fine-tune the full model, so all the parameters, like this 300 million parameters, or you just say, well, I'm actually training just one layer of the encoder. So you freeze all the parameters from the input up until pre-last layer, and then you just fine-tune on your task, like sentiment classification, just the remaining a fraction of parameters. So it saves your time, saves resources, and surprisingly it works. So you can really fine-tune just parts of BERT if you have enough data. So this is one let's say one technique they use for this fine-tuning. So just the final fully connected layers of BERT. So this is a standard thing. And another very interesting take on fine-tuning transformers or for domain adaptation is so-called adapters. So if you never heard about adapters, we don't have to spend time on that, but I just recommend this paper from ICML, was it? ICML, yeah. ICML 2018. So adapters means that something like fine-tuning just one layer of BERT, but with adapters, you plug some, so if these were BERT, and there are some layers in there and self-attention and blah, blah, blah. So you basically plug one adapter layer here in each block maybe and just train these parameters, and the rest is frozen. So this is basically plugging some adapter into the architecture of BERT or any other transformer. You train the full model. You don't train to full model, but you just need these, you train these kind of just intermediate layers, which means you can save time. So these, the adapters and encoder blocks of the transformer, and you only train a few parameters of the full size of the model. So you save a lot of storage as well. And if you read this paper, you will see that transformers, that adapters are actually super efficient for some tasks for fine-tuning. So it's faster, small footprint, and efficient. Okay, so these two approaches are, they use them, and obviously, in this kind of bottleneck here, you don't have to save the full BERT, but save the adapters and save the final connected layer. So which means you save a lot of time for each slice, a lot of space for each slice, so it makes it also efficient. That's it. I mean, it looks like pretty straightforward. Actually, I think the paper is somehow straightforward. You take the technique and just to try to make it more efficient. That's fine, but I guess it's really important to see that it's how far can you get with this CISA approach in some particular NLP task. And the last paper I want to show is from, I think, these are people from Stanford, if I'm not mistaken. Unlearn what you want. So, and basically they're taking, not really like the CISA approach is a different one. So I guess there is no guarantees in there, but basically they trying to plug, so this is the one block of transform model. And they are plugging here the unlearning layer. So this is something like adapters, I guess. I think maybe it was parallel to the editors, the CISA editors thing. And they're trying to learn, overall unlearning layers are plugged in transformer layers after a feed forward. During training, only the unlearning layers are learned to forget requested data. So basically, this sounds to me like something like an adapter, but I'm not 100% sure. I didn't read the paper in very much details, but it's another approach to do some unlearning here. And then they are kept for each data point, and they are somehow combined in the predictions, I guess. This is something, it could be this fusion, could be something like averaging of parameters. I'm not 100% sure, but it goes like, the thing we're talking about, combining parameters of different models together. It's also called fusion sometimes, if I'm not mistaken. So anyway, I just want to highlight like this CSAP approach is one of those, but there are other ones which are just, trying to dig deeper to the architecture of the transform models to learn and unlearn or learn particle parameters on the baseline model and not a full model. And then it's easier to unlearn because you have just much smaller footprint of the parameters to be unlearned. Having said that, I think we reached the end of the lecture. So any questions to unlearning? Yes.
So since that requires that I have the training data right now,
You-
I train model. So
Exactly.
somebody uploads a model, which is common for some people.
Mhm.
I can't download it and remove or unlearn something with it.
Yeah, so if you have if you have a trained model and you don't have access to the training data and you want to unlearn this data from the trained model, you're getting into troubles. And one of the way could be this epsilon delta unlearning thing, maybe, but you would also need, I mean, here in this, just if this were just a convex model, like all these assumptions were set, you would still need some sort of statistics of the data, which you never have as well. I mean, if somebody uploads a model, so I don't think you have any chance, to be honest, like formally, yeah, but.
So in the next slide, I think that for the unlearning method.
This one.
No, for the unlearning method in the formal version.
Yes.
We saw that the unlearning method is also used for learning from zero. So
Okay, this one. Okay. Now, if you would be retraining from scratch. Okay, so we have this. So what was the question?
the other method is also the same method for learning.
No.
Okay.
No, the unlearning method takes a model. So learning method,
Yeah, because
Yeah.
there in the right
Here?
part,
No, here, yeah.
animation,
Yeah, okay, that's interesting. So, what's the signature of this function? That's an interesting part. I think, well, there is a learning. Okay, well, let me see. What is the A? I don't see where. No. I mean, the learning method is something which is not here. So there is no learning method. You have the learn model. So this is a bar, right? I mean, I would have to delete this, but this is a bar and a bar. So these are the same functions. These are unlearning functions. But one of them works on the trained model on the full data set, and one of them works on the trained model on the smaller data set. This is the difference.
there is no model that is in function.
So this A is a trained model. This is trained model. Right, and this. So here, suppose we have output the model AS. So in one case we have A on the training data, and in the other we have A on S minus U. But this is the trained model. I think they should call that like I don't know, like a W and W minus U or something like that would be mine. It's a choice of naming in mathematics is is an art. Okay, does it make sense now? Okay, cool. Good. Any other question on unlearning? If this is not the case, let me just stop recording right now.